Hello. In this lecture, we're going to talk about a few things that you've already seen in Physics 358 that'll come back and be important in statistical mechanics. We'll have a couple of conceptual ideas and then a couple of mathematical techniques, all of which are going to be important throughout this course. If I go over things too quickly or don't give you enough detail, you can certainly ask questions in Piazza, but I'll also point you that all of this is drawing from chapter 2 of the text. So again, something that you already saw in 358, I just want to be sure everyone's refreshed and ready to go on these. So the first concept I want to talk about is equilibrium. And this is a fundamental assumption that goes into basic stat mech. Okay, so what is equilibrium? An equilibrium state is when macroscopic variables of the system become constant, but the microscopic variables can still be dynamical. So as one example that you saw probably a number of times in the past is gas in a cylinder, right? So we've got some cylinder and there's a piston that can move in and out of this cylinder. If the piston is fixed, and I don't mean held in place by bolts, but if the piston was moving and is now stopped, that's a mechanical equilibrium. So the macroscopic variable is the position of the piston, or the pressure on the piston. If you assume outside is atmospheric pressure, this has now come to mechanical equilibrium in the sense that the pressure inside and the pressure outside are the same. So while this is mechanical equilibrium because the piston is not moving on a macroscopic scale, of course, if you look inside of the gas, all of these molecules are moving rapidly, bouncing off the walls, and in particular bouncing off of the piston. That's the source of the pressure. Right? So microscopically, there's a lot of dynamics, but the macroscopic variable, which is the piston's position, is fixed. Now, if you look extremely closely, you might see that the piston is fluctuating because it's being hit randomly from one side by the gas inside the cylinder. It's being hit randomly from the other side by the atmosphere. Or if there was some spring holding it and the molecules inside hitting it. The point being, it could be fluctuating microscopically, but on a macroscopic scale, if you just step back and look at it, you don't see it moving. So that's a mechanical equilibrium. Another type of equilibrium you may be familiar with is a chemical equilibrium. So in that case, you might say, some chemical reaction proceeds until you have 2 moles of sulfuric acid and 1 mole of, I'm not a chemist, let's call them A and B. So you've got some quantity of chemical A and some quantity of chemical B. Okay. Now, when you come to chemical equilibrium, that means the concentrations of those 2 chemicals stay fixed. But just because the concentration, the macroscopic variable, is fixed, doesn't mean every single molecule of chemical A retains its nature as a molecule of chemical A. There will be reactions going back and forth on the molecular scale, and A turns into a B, back to an A, and so forth. The equilibrium means that the macroscopic variable, the concentration, becomes constant. A third type of equilibrium that'll be important for us is thermal equilibrium, and that's where energy has stopped sort of moving in or out of the system. So macroscopically, the energy of the system is fixed. But of course, if it's in contact with a heat bath, then energy is actually flowing back and forth between the system and the heat bath. But the total energy content of the system, which is connected to the temperature of the system, that'll remain constant. So those are 3 types of equilibrium. And we're always in this course going to assume that we're looking at an equilibrium system. Now, there are more advanced techniques that you can learn in statistical mechanics that look at non-equilibrium situations. That's actually sort of a cutting edge in research today, and has been for decades at this point, because the non-equilibrium case is harder. So continues to be a subject for research, but many of the approaches to non-equilibrium systems build from the techniques you've learned in equilibrium statistical mechanics. So even if you said, geez, equilibrium's not very fun, I want to go learn about things that are out of equilibrium, you need the foundation in equilibrium statistical mechanics to build from. Now, there's, actually, I don't know who this is from, but someone had said along the way, you know, the only equilibrium in life is death. Okay, which is maybe a bit morbid, but the idea being most of the systems that we find really interesting are interesting because they're out of equilibrium, right? Life is not an equilibrium process. There's a constant flow of energy into and out of, matter into and out of, and so forth. So a living creature is not at equilibrium. So you might say, geez, if all the interesting stuff is non-equilibrium, why do we bother? And the answer is no, not all of the interesting stuff is non-equilibrium. And in fact, a great many systems can be treated as approximately in equilibrium. So there's equilibrium systems. Those are great. We can study those quite robustly. But then sort of the next step would be things that are almost at equilibrium. And just as an example, when you look at something like a hydrodynamic system, you might say this system does have some bulk flow, so it's not at equilibrium proper, it's not at mechanical equilibrium, but locally it's at thermal equilibrium, right? So that the energy content of a small part of the fluid is fixed, and so you could define a temperature for that local part of the fluid, and that's true sort of every local part. And there's actually quite a lot you can learn and build from in that regard. So equilibrium is both fairly common and also the foundation for non-equilibrium physics. And so that's where we're going to spend this term. So the second concept is actually pretty concise, but it's what Schroeder in the book calls the fundamental assumption of equilibrium statistical mechanics, which is quite a lot to say, but I think it's a fair thing to say. And the way he words this, I like, because it's carefully worded. He says, in an isolated equilibrium system, all microscopic states are equally likely. So we just talked about equilibrium. Okay, isolated means that there's in fact not any flows across the boundaries of the system. Okay, so if it's isolated, it's not in contact with a heat bath, for example. Or you have maybe two parts that collectively you consider as a whole system, and then maybe you want to analyze one part as your system of interest and one part as the heat bath, but overall the system that you're looking at is isolated. Okay, so in an isolated equilibrium system, all microscopic states are equally likely. And by microscopic states, we mean now really accounting for every single particle and exactly what it's doing. So something we'll never do in practice in an experiment, but what we want to do conceptually so that we can do statistics on those microscopic states. So in some sense, what this is telling us is we're going to want to count these microscopic states, because if we're looking at an isolated equilibrium system, each individual microscopic state is equally likely. And so the way that we can build statistics is to say, well, how many microscopic states correspond to a particular macroscopic state of the system? If I'm at this pressure and this temperature, how many different microscopic states are possible? So we're going to then move into mathematical ideas, and these mathematical ideas all focus around counting, because counting is how we're going to be able to do statistics on large numbers of particles. So now we're going to go on to the mathematics of counting, also called combinatorics. This is a very rich field of mathematics. We're just going to cover a couple of simple techniques that come up a lot in StatMech, and that you already saw briefly in Physics 358. I'm going to go through the math pretty quickly, because you can pause me, rewind me, play through again if you missed something the first go around. All right, let's jump into it. So the first sort of technique that we'll see a lot of is combinations. And so a combination is written like so, and the way that a lot of people read this is n choose r, right? So if I've got n objects and I want to choose n of them, that combination n choose r is how many different ways can I choose r objects out of a total set of n. So it takes the form n factorial over r factorial n minus r factorial, and we'll write it most of the time in this slightly more compact form. It's called a binomial symbol because they come up in the binomial expansion. And it's sort of intuitively what's happening here in this is n factorial is saying how many different ways can I take those n things and put them in order, right? And I'm going to call my combination, well, I've selected the first r of these are the ones I've selected. So n factorial is the total number of ways I can order them, but the actual orders within the first r and the last n minus r don't matter. So you divide by r factorial, in other words, how many ways I can order the first r of them, and n minus r factorial, how many ways I can order the rest of them. That's sort of an intuitive way to understand what's happening with the combination formula. As an example of this that comes up a lot in physics, you can think of a paramagnet, or really any spin system, but we'll talk about a paramagnet because it's a simple case. So in a paramagnet, you have atomic spins that either want to be aligned to a magnetic field. So you apply a magnetic field, and maybe depends on the material, but let's say this is a paramagnet where they want to align with the field. So the spins that are pointing up are at lower energy. They're in the direction they want to be. The spins that are pointing down are at higher energy. And now, if we want to know about the energy, what we need to do is just say how many of them point up, how many point down. So this n with an up arrow is the number of spins pointing up. Okay, so suppose that we know n up equals n over 2. I wrote a question mark here, not because I don't know what n up is. I've said let n up be n over 2, but rather my question is, how many different ways can I do that? And this is a combination problem because we have n spins, and we want to select n over 2. We want to select half of them and say those are the ones that point up. But we care which particular ones are pointing up. So this would be n choose n up, or n choose n over 2, which we've got here, and just plug in the formula. Great. So it's n factorial over n over 2 factorial, and then n minus n over 2 is also n over 2, so an n over 2 factorial again. And one thing that you'll notice from this is n choose r is equal to n choose n minus r, right? The formula is sort of symmetric about that change. And in the case of the paramagnet, what that implies is that n choose n up, right? The number of ways we can, the number of microscopic states with n up number of spins pointing upward is equal to n choose n minus n up, which would be how many are pointing down, right? So it's n choose n pointing down. And physically, this should be the case, right? If I ask how many states do I have with n up spins pointing up, it better be the same as the number of ways I can have n down spins pointing down. And that's the case. Okay, so the math sort of just makes sense there. Good. Okay, the next counting task. So the simplest would just be I've got n of these things and I want to pull r of them out. Okay. The next simplest would be to say, suppose I have a bunch of bins. Say I've got n bins. And I've got a bag full of balls, I've got m balls, and I want to put those into the bins. Okay. How many ways can I do that? And basically what we do is we say, if my question is, how many ways can I put m balls into n bins? And now that I'm saying it out loud, I realize that's a terrible choice of variables, but it's written here. You can see it. You know which one I mean. So I've got m balls, and I want to put them into n bins. this is something we transform into a problem of ordering m balls and n-1 sticks. So this is why I've called this ball and stick counting. So really, like the problem I have in mind is counting how many ways can I fill bins. But we transform this into how many ways can I lay down balls and sticks in a row. And I'll show you how. So as an example, suppose I have 4 bins, and I haven't told you how many balls I want to put in them, but just the way that I demarcate the bins is by putting a stick between the bins, right? So if I have 4 bins, I only need 3 sticks because I'm just marking the boundaries between the sticks. So I'm going to need n-1 sticks to represent n bins. So what I will do is lay out a total of m plus n-1, right? So my total number of things, balls and sticks. And then I'm just going to choose where I put the sticks or where I put the balls, because that's symmetric, just like we talked about up here for the paramagnet. So of my m plus n-1 total positions, I'm going to choose m of them. I'm going to choose where I put the balls. And that completely determines the counting, because if I put the m balls down in those positions, the other n-1 have to be sticks. Okay. So if I want to count how many ways I can put balls and sticks together in a line, this is the formula, right? Either. And now, how does that look in practice if I'm saying, okay, let me represent a specific configuration of balls separated into bins. So here I've got 6 balls, and I'm separating it into, well, there's 3 sticks, so 4 bins. So I just count how many balls I have until I hit the first stick. 1, 2, 3. There's 3 balls in the first bin. There's 1 in the second bin, none in the third bin, and 2 in the fourth bin. Okay. A set of 4 empty bins would just be 3 sticks. Okay. So that idea is how we say, convert from bins and how can I fill bins into this simple combination formula. An application of this in physics would be Einstein's solids. So this was something that you learned about last term, or whenever you took 358. The idea of an Einstein solid, it's a simple linear model of a solid. It says, suppose I have a huge number of harmonic oscillators, and I also have a huge number of excitations of the oscillators. So you can think of this as like the atoms in a crystal, right? Each atom in a crystal feels something that's a bit like a harmonic potential, because if it moves this way, it gets too close to the atom on this side, it feels a repulsion. If it goes this way, it feels the atom on the other side and feels a repulsion. So you end up with at least approximately a harmonic potential. So if each atom is a harmonic oscillator, and you can put different numbers of excitations in those oscillators, the question would be, how many microscopic states do I have for a specific excitation energy? Cats are back under control. Let's try that again. So for a specific excitation energy, E, we'll say the oscillator frequency is h bar omega, and we have Q total excitations. So our oscillators are our bins, or our atoms are our bins, right? So this atom is sitting in a harmonic potential, and we're going to ask how many excitations do I put on each atom? And that's the real count is for our total number, how many different microscopic states can we make? Since we're saying that the atoms correspond to bins, so there are N, capital N atoms, so N bins, and Q total excitations, so Q balls. So this is a ball and stick problem. N plus Q minus 1, choose Q. And this omega is the symbol we're going to use for the total number of microscopic states. Okay, so in this case, for the Einstein solid, it comes out as a combination, again, using the ball and stick counting. Okay, the last combinatorial thing I want to go over is Stirling's approximation. So Stirling's approximation is how we deal with all of the factorials that are going to come out of these combinations, right? Every time we do a combination, we get 3 factorials. Okay. So if we were working with small numbers like 5, you can write it out by hand, get your answer. If we were working with slightly larger numbers like 27, we could put it into a calculator and get the answer, and it's quite big. Even for 27, it's bigger than 10 to the 27th, right? It's 10 to the 28th. So when we look at a solid, we're looking at like a chunk of stuff. And if you remember, a mole is 6 times 10 to the 23rd atoms. So we're going to be looking at factorials for things that are like 10 to the 23rd. Yeah, you can't just put that into your calculator. So we need a way to approximate these things, because at the end of the day, right, I didn't write out the entire value for 27 factorial. It's got 29 digits. But I don't need to know it that well. I probably even wrote more digits than I need to know really for 27 factorial. So if we have a good approximation, we'll be able to use that instead of this sort of hopeless amount of multiplication. And the answer is something called Stirling's approximation. So Stirling's approximation says for large n factorial is approximately n raised to the n times e to the minus n times the square root of 2 pi times n. Okay. And frequently we say, geez, n factorial is such a huge number. Even sort of analytically on paper as a formula, it's hard to think about, hard to work with. And so a lot of times we'll be looking at the logarithms of these large factorials. So you can just take the logarithm of this and say, okay, the logarithm of n factorial is, let me warn you, I will not be able to break this habit, so I'm just going to explain it to you and we'll go from there. When I write log, what I mean is the natural logarithm. It's the logarithm in base e, which most people write as ln. My undergrad degree is in math, and I came from a very strong feeling that the only logarithm that deserves the name is the natural logarithm. And so I write log for the log in base e, for the natural logarithm. If it's a log in any other base, like 10, which of course is cosmically important because we have 10 fingers, I will explicitly put a base. So if you see log, that means natural log. And I apologize if that's confusing, but if I tried to break myself of the habit, it would be dramatically more confusing because I would just go back and forth between ln and log. So just know anytime you see log, it means the natural logarithm. Okay, with that apology aside, we're frequently going to need the logarithm of large factorials. And so this gives us the logarithm, just by taking the logarithm of this expression, n log n minus n. This is where, see, natural logarithm of e to the minus n is just minus n, so that's what I mean by log, plus a half log n. And I've left something out, right? So this is square root of n and the square root of 2 pi. I didn't write the plus log of 2 pi. That's because that's tiny, okay? So Stirling's approximation, like this formula, including the 2 pi, Stirling's approximation is only good for large n. And by large, at the bare minimum, we mean bigger than 2 pi. And so n times log n for n much bigger than 2 pi will be dramatically bigger than the logarithm of 2 pi. So we just drop the constant when we take the logarithm. And in fact, usually we're talking about n's that are so big that even the 1/2 log n is kind of, negligible by comparison. And so frequently we'll be using even just this as our approximation for log of n factorial. That's, again, if n is 10 to the 23rd, just using this is a phenomenally good approximation. And 10 to the 23rd times the log of 10 to the 23rd well, it's 10 to the 23rd times bigger than the log of 10 to the 23rd. So it's an extremely good approximation for the kind of numbers we work with in statistical mechanics. So now we want to take these mathematical techniques and put them to use. And what we want to get to, again, seems like a pretty big statement, but it's why statistical mechanics works at all. And what I mean by that is we know from classical mechanics that the three-body problem is already sort of an extremely difficult problem. So you might expect going to 4, 5, 6, this is just going to get more and more complicated. So why is it that going to extremely large n suddenly makes the physics simpler? And the idea is that we get rid of our microscopic but complete description and move to a statistical description of the microscopic physics, which then gives us macroscopic answers. And what we're going to see is why those macroscopic answers get better and better as n gets bigger and bigger. So we're going to be taking Stirling's approximation here and using it quite a lot, and we'll get some nice results at the end. So I want to do this for a specific system, which is, again, this Einstein solid. So a system of oscillators and excitations. And in particular, we're going to look at the high temperature limit for the Einstein solid. Now, one of your problems in the problem set looks at the low temperature limit, and the sort of mathematical tricks that you use for that problem are almost identical to here. Okay. Once you take very large numbers and take their logarithms, then you can deal with hierarchies that say, like, in this case, we're looking at high temperature, which means the Q, okay, the number of excitations, is much larger than the number of oscillators, N. Okay. Or another way to say this, it's high temperature because the average number of excitations per oscillator is much more than 1. Okay. So to start with, let's just remind ourselves the Einstein solid. Its number of accessible states for n oscillators and q excitations is this combination, n plus q minus 1 over q, or n plus q minus 1 choose q. Should be careful not to say over so you don't think we're talking about a fraction. And you'll notice I've put subscript a's on all of these. The reason that I've done that is a bit of tipping my hand to where we're going. We're going to talk about, at the end, two Einstein solids stuck together and what happens to the microscopic description when you put two of them together. Okay, so we're going to start with just the one, which we'll call A. Shockingly, the second one will be called B. Okay, so we know that it looks like this, and in particular, we've got these minus ones floating around that are just sort of a bookkeeping nuisance. And what we'll do is we'll drop those ones. And what I want to demonstrate first is just that this approximation is in fact quite good. Now you might think, if n and q are both extremely large numbers, dropping the 1 really shouldn't matter. That's like a standard way that you would think about perturbations. It might feel a little different this time because we're dropping it from a factorial function, right? So it's not just that I'm subtracting or adding 1 to a big number. What I'm actually doing in going from here to here is I'm multiplying by n plus q. N and q are both big numbers. I'm multiplying by a very big number. That seems like that might be, a bit dangerous. I'm also dividing by n. So I'm going to call this omega prime just for the moment so that we can see how it differs from omega. And I'm going to immediately take the logarithm. Now, this is something that we're going to do a lot of because the number of microscopic states, omega, is frequently going to be a tremendously large number, right? So the number of atoms, if it's something like Avogadro's number, is already a very big number. And the number of microscopic states is frequently going to look more like e to the number of atoms. Okay, so it's going to be something that looks like e to the 10 to the 23rd. So these numbers are so big, we sort of just don't want to deal with them on their own. We want to look at their logarithms. So the logarithm of omega a, I'm going to use Stirling's approximation here. So this is for the factorial on the top, n log n minus n. So I've just factorized this to make this bit look a little simpler, a little more compact to write. You can see this more easily if you look at the other factorial here for q factorial. We've got minus q log q minus q. Okay, and again for n minus 1. Now, that's our approximation for log of omega. If we take the difference of log omega and log omega prime, the difference of two logarithms is the logarithm of the ratio, right? So this is log of omega over omega prime, and that just picks out the two factors I identified up here, na plus qa and na. So what you see is the difference between these two is the logarithm of a ratio of large numbers. That's going to be quite small compared to the large numbers themselves. As I was saying, you have very large numbers compared to their logarithms. And if you take the logarithm, for example, of Avogadro's number, right, 6 times 10 to the 23rd, the log of Avogadro's number is about 100. Okay, so almost 22 orders of magnitude difference between the number and its logarithm. So when we look at this difference being just a logarithm, and not just a logarithm of a large number, but a logarithm of a ratio of two large numbers, that's going to be dramatically smaller than the actual values up here. So this is, in fact, an extremely good approximation for any system that we're going to care about. Okay, good. All of that is a long-winded way of saying we don't need to put these minus ones in anymore, but this technique of taking the logarithm, looking for expansions and differences, that's going to come up a lot. Okay, so now we want to look at the high temperature limit. And as I sort of said before, high temperature means Q is much, much bigger than N, right? So we have, on average, much more than one excitation per oscillator. So we have this form for omega that we're going to use, Na plus Qa factorial over Na factorial Qa factorial. We take the logarithm, and again, we factorized the Stirling approximation as we did before. Now we need to use the fact that one of these numbers is bigger than the other. And again, when you do the homework and look at the low temperature, it's going to be that Na is much bigger than Q. In the high temperature limit, Qa is much bigger than Na. So just as an aside, let's look at this piece, just this logarithm. Okay. So since Qa is much bigger than Na, let's factor Qa out, right? And the logarithm of a product is the sum of the logarithms. So this is log of Qa plus log of 1 plus Na over Qa minus 1. And whenever you have the logarithm of 1 plus a small thing, which is what we have here, you can Taylor expand that it's just the small thing. So in other words, the log of 1 plus x is just x when x is very small. So this becomes log of q, or log of Qa, plus Na over Qa, and we pull the minus 1 through. Okay. So, and just to compare to what we did up here, 1 compared to a very large number, or sorry, 1 compared to a large number is definitely small. 1 compared to the logarithm of a large number is not necessarily so small. So we don't want to make that assumption. We'll keep the 1 around. All right, so taking this and now rewriting the logarithm of omega A that we had up here, we put the expansion in that we did, and now we want to look at what cancels, because a lot of things cancel. Okay, so first we've got Na times log of Qa, that's going to pull through. We've got Na times Na over Qa, that's here. Qa times Na over Qa, that gives us just Na. Now, the Qa times log of Qa is going to cancel with Qa times log of Qa here. We're going to get minus Na plus Qa. Here we're going to have a plus Na and a plus Qa, so those cancel. And finally, we have Na log Na that doesn't cancel against anything, so that comes down. Okay. And then the last thing we're going to do is we're going to actually, let me mark it out for real, we're going to ignore this term. And the reason we're going to ignore that term is we've said Q is much bigger than N. So this term is much smaller than this term, which we're retaining. And each of them will probably be a bit smaller than these guys because these do have logarithms of large numbers multiplying Na. So finally, we can put this all together, re-exponentiate it, and for the multiplicity of our high temperature Einstein solid, we get QA over Na, right? If it's difference of logarithms, it's the log of the ratio. So QA over Na raised to the Na. And then this guy is just going to give us an extra e to the Na. Put it all together. This is our form. So this is going to be a useful form that'll come up several times here. Okay. Next, we want to do what I hinted at before, which is to think about two Einstein solids, solid A and solid B, that are in thermal contact with each other. So if they're in thermal contact, that means they can trade energy back and forth. And in the Einstein solid, the energy is in the form of these excitations. So we say there are some number of excitations QA in solid A, QB in solid B. Those numbers can change, right? Excitations can hop back and forth between the two solids, but the total number, Q, which is QA plus QB, that's going to be fixed. So fixed total energy, it's an isolated system, but it can send excitations back and forth between the two. And we'll define the total number of oscillators as just Na plus Nb. Okay. When we want to look at the multiplicity of this system, it's just the product of the two multiplicities, right? So for any possible state of A, right? So I'm going to say the number of excitations in A is QA, and I'm going to fix a particular microscopic state. Like, okay, 5 excitations on this oscillator, 12 on this one. So some microscopic description, some microscopic state of A. Then I could have any of the possible microscopic states of B. So there would be omega B of those. Now take the next state of solid A. It can also have any of the microscopic states of B. So again, omega B adds up, you get omega A times omega B. Okay. So when you take the number of states, number of available states of a pair of systems stuck together, it's just the product of their individual states. Great. We've got a formula for that up here. We can just plug in QA, NA, QB, NB. And now to make this a single variable, right, because QA and QB are both variables, but they're related to Q. So I'm just going to rewrite QB as Q minus QA. So now we've written this in terms of one variable, which is really what we had all along, right? If we knew QA, we could immediately say QB because it's just Q minus QA. Okay. And again, we're going to do this all the time. This is a really big number, right? This is something raised to the NA, which is already a big number. So let's look at the logarithm. So the log of this, just separates again. Log of a product is the sum of the logs. So this becomes NA log of QAE over NA plus NB log of, again, we want Q minus QA E over NB. Okay. Now, why did I want to write it in terms of a single variable so explicitly? Because what we're interested in here is, in fact, the distribution of numbers of microscopic states. Okay. So what do I mean by that? If I know QA, say there's 500 excitations on solid A, since Q, the total number of excitations, is fixed, I know QB, but there are a lot of microscopic states that have 500 excitations in solid A. So I want to know the number of states as a function of QA. Okay. So you can imagine if all the excitations are in one side or the other, right? So if QA is 0 or Q, there should be fewer possible microscopic states. It just sort of makes sense, right? There's less places to distribute them if they're stuck on one side. But we'd like to go from just that sort of qualitative understanding to something quantitative. And that's what we're going to do here with looking at the distribution of omega. Okay. So we've got omega as a function of QA, or rather its logarithm. Now what I want to do is say, first off, where is omega highest? In other words, what value of QA leads to the largest number of accessible microscopic states? Because if you recall, that at the beginning of the lecture we talked about this fundamental assumption of statistical mechanics is that all microscopic states are equally likely in an isolated equilibrium system. We're looking at an isolated system, so every state is equally likely. Let's find out which QA has the most microscopic states available. Okay, so take the derivative of the log with respect to QA. This term is going to give you NA over QA. This term, pick up a minus sign, you get NB over Q minus QA. And if we set that equal to 0, that should tell us where the maximum of this function is. So follow it through. So QA star is what I'm calling the maximum point, and it's just the total excitations times NA over N. Okay. Now that should make some sense, right? We're going to have the most accessible states when we've sort of evenly distributed the excitations between the two sides. And by evenly, I mean we have the same number of excitations per oscillator on each side. Okay. Excitations per oscillator is going to be a proxy for temperature here. And so in fact, what this is really saying is the largest number of microscopic states is available when these two are at equilibrium, when they have the same temperature, the same average excitations per oscillator. Okay, great. So now we know where the maximum is. Let's go further. Let's take the second derivative, because what I'd like to do is just look at the shape of this distribution around Q star. Okay, we know where the max is. How does the distribution look near the max? Okay, so we take the second derivative. This is going to drop down and give us Q squared in the bottom. Same story here. We've got two minus signs, so this stays minus. Okay, so the second derivative, now if we plug in the value for QA star, right? We're doing a Taylor expansion here. Plug in the value of QA star from here, and this reduces down in the end to n cubed over NA NB Q squared. Okay, so first of all, we've got a negative second derivative. That's good. It should be a maximum. Negative second derivative means it's a maximum. And now we can write out, again, the Taylor expansion for log of omega. So we've got the value at Q star. First derivative is 0 at the maximum. So then we get the second derivative with a 2 and QA minus Q star squared. Okay, so now we've got a form for the log of omega, and let's exponentiate it and get back to omega. So omega ends up looking like QE over n to the n. If you remember, that's suspiciously like the oscillator equation. So this has sort of as many microscopic states available as if the two systems together were a single oscillator when QA equals Q star. And sorry, I forgot to mention one thing, which is in going from this line to this line, there's a bunch of things that are a bit messy here, and just to make it easier to follow the math through, I'm going to assume that NA equals NB equals n over 2. So Q star is now n over 2 over n, which is to say Q over 2. And this mess of n cubed over NA, NB, 2, this all reduces down to 2n over Q squared. Okay, so it just makes the math a little easier to follow. And now we've exponentiated, and as I said, we have the available states of the complete system times this exponential suppression as you move away from QA equals Q star, which again in this case we've now said it's Q over 2. This is suppressed like QA minus Q star squared, which probably you've encountered before. This is a Gaussian. or what's sometimes called a bell curve. And Gaussian has this form, right? So this is just a normalization factor. The good stuff is up here in the exponent, x minus x star, where x star is the most likely value, over 2 sigma squared. And what these end up meaning, so it's called a bell-shaped curve because it looks more or less like a bell. Okay, it's got a strong peak in the middle that falls off in this exponential fall off. X star is the peak, and the curve is symmetric about x star. And then that sigma in the denominator of the exponent, that tells you the width of the distribution. Okay. So if we compare this guy to this form, we can pull out, well, value of q star we already know. qa star is q over 2. And sigma a is q over 2 root n. Now, q by assumption here is much bigger than n, so q over root n is a very big number. But q over 2 is a much, much bigger number, right? So they differ by square root of n. Said mathematically, the width divided by the position of the peak is 1 over root n. Okay. So what that means for us is when we take n to be very large, if we think we know what the macroscopic state is based on this q star, right? So we know macroscopically there's this much energy on side A and this much on side B. That's what picking QA means. The uncertainty in that statement is going to be on the scale of 1 over root n, right? So if we've got, again, Avogadro's number of particles, and we say, hey, the temperature on this side is 100 Kelvin. They're at equilibrium, it's 100 Kelvin. What's the uncertainty in that statement? Well, it's 100 Kelvin divided by the square root of n, which is to say the uncertainty is like 1 in a trillion compared to the temperature. Okay, so that's what I mean by this is why statistical mechanics works. When we make these macroscopic statements in equilibrium, they should generally, and I'm going to say generally because we'll find some cases where this may not be quite right, but generally they should be accurate to within 1 over the square root of the number of particles. So as we take the number of particles to be very large, the approximations of StatMech will get better and better. Now just to think slightly smaller, even if n is say 10,000, we're looking at a collection of 10,000 particles. We'd already say that the predictions of statistical mechanics, generically we expect them to be good to 1 over the square root of 10,000, which is to say good to within 1%. So for an awful lot of cases, we don't even need n to be particularly large to feel like we can make good predictions. Okay, so one last thing. I know we've covered quite a lot in this lecture. Again, I feel like I can get away with it because this should all be review, but feel free to ask questions. In fact, I encourage you to ask questions in Piazza if anything is unclear or if your memory is still a bit hazy. So the last thing I wanted to just mention is that a lot of the reason we're doing all of this state counting is to get to this final conclusion that is here. So entropy is something that you know from thermodynamics is an important physical quantity. You've probably already talked about that it somehow quantifies the disorder in the system or the information in the system. Those are both ways to describe this. And the connection is, this was Boltzmann's big insight, that the entropy of a system is related to the logarithm of the number of accessible states. So again, that number is so huge, we don't like to deal with anything but the logarithm if we can avoid it, and it turns out nature is the same way. So the entropy, which is a very sort of physical quantity, it tells you why you can't make a perpetual motion machine, right? It's why you can't just have a perfectly efficient heat engine. That turns out to connect exactly to the counting of microscopic states. And the only thing you need to know other than the logarithm is this constant out front, Boltzmann's constant. And I have conveniently forgotten to put units on this. So let's do that. What are the units of Boltzmann's constant? It is joules per Kelvin. And you can now see that my handwriting on vertical surfaces is terrible compared to on a flat surface. That'll hopefully get better with time. All right, so that's Boltzmann's constant. This tells you how to convert from, well, in this case, from a dimensionless quantity, right, the logarithm of a number, into entropy. And just as a quick example, in an Einstein solid, which is what we've been talking about for a while now, we know the form for omega is QE over n, all raised to the n. And when you take the logarithm of that, that exponent comes out front. So the entropy is nk times the log of, I'm just going to say some stuff, though the stuff ends up being related to temperature. The important thing is that entropy is an extensive quantity, which you should have discussed already in thermodynamics, right? An extensive quantity is just one that grows with the system, right? The energy content of a system is extensive. Bigger system's going to have more energy, whereas the temperature is intensive. It's more of a measure of the energy per particle. So similarly, entropy should be an extensive quantity, and at least in this case that we've been looking at, we can see, yes, that's correct. Okay, in case somehow all of that has not already exhausted you, I wanted to give you this small bonus at the end. Bonus in the sense that like this won't be on the problem set or anything. But I noticed that Schroeder doesn't give an actual derivation of the Stirling formula. And I think it's something you can handle at this point, but also it actually uses one of the ideas that we've used already in this lecture, which is expanding an exponent in a Taylor series so that you get a Gaussian, which it turns out Gaussians are very easy to work with. Essentially, certainly in intro statistical mechanics, if we come upon a probability distribution, we will assume it's Gaussian, or we will find a way to turn it into a Gaussian. So a little extra practice with Gaussians doesn't hurt. So if you have seen it before, the factorial is related to something called the gamma function. And they're related by this sort of very simple formula. You might say, why do you need to give factorial another name? So factorial and the gamma function are related by this formula when n is a non-negative integer. Okay, so 0, 1, 2, 3, and so on. But the gamma function is actually an analytic function. It's defined on the whole complex plane. Has a lot of interesting properties that we're not going to talk about. But there is a nice integral formula for defining the gamma function. And that's what we're going to use to derive Stirling's approximation. Okay. Now, if you haven't seen the gamma function before, you can ignore that and just look at this equality. And again, if you've not seen this before, I'd invite you to just play around with this a little bit. If you do integration by parts, you will see that you can prove that n factorial equals n times n minus 1 factorial. And you can also set n equal to 0 and do the integral to see that 0 factorial is 1. And so you'll see exactly the connection between that integral formula and the factorial function. So I have now rewritten this as e to the minus t plus n log t. Okay, same formula, but now everything's in the exponent, so we can play this trick of Taylor expanding the exponent. Okay, so I'm just going to define f of t is the stuff that's up here in the exponent. F prime is minus 1 n over t. So the maximum of that function, again, extremal point, but it's a maximum. When you set this equal to 0, you just get t star equals n. Second derivative, the 1 goes away, and we just get minus n over t squared. So near t equals n, we can Taylor expand f into, well, its value when t equals n. So just n log n minus n. Looks promising. That looks familiar. And then minus, again, derivative 0, so there's no first order term in the Taylor expansion. The second order term is a half n over n squared is just 1 over n, and then t minus n squared. Okay. So that's what we've gotten out of this exponent when we plug it back in, right? E to the n log n is just n to the n. E to the minus n is e to the minus n, and we carry down the quadratic term as well. Now I've separated this piece from this piece because this bit has no dependence on t. And so when we go to do the integral, that part's just going to pull right out. Another notational thing that I should mention, you may have been confused up here because I just wrote integral 0 to infinity dt, and there was nothing between the integral and the dt. Much like the fact that I write log and mean natural logarithm, I always write my integrals this way, like it's an operator acting on the function after it. So this is the integral of t to the n e to the minus t dt. That's probably how you saw it written in sort of your intro to calculus courses. This means the same thing. And again, if I tried to write it the other way, I guarantee I would do it differently all the time and it would be more confusing. So just remember, when I'm writing an integral, this is like an operator acting on the function next to it. So in particular, if it's a big function, I'll put it in braces so that you know this integral is acting on this stuff. Okay, so here we've just rewritten this thing with our Taylor expanded form. Again, these two bits don't depend on t, so we can pull them out. So we've just got the integral from 0 to infinity of e to the minus 1 over 2n t minus n squared. Again, this is a Gaussian. And I'm going to now say, hey, if it was the integral from 0 to infinity, I don't know how to do that for a Gaussian. Or I don't know how to do it in terms of elementary functions. I can call it the error function or the complementary error function. That's not terribly helpful. So I'm going to say this looks a lot like the integral from minus infinity to infinity. Now, why can I do that? I've added the whole half of the real line to this integral. Why would I think that that should be almost the same? The reason is exactly what we talked about with why does statistical mechanics work. Namely, I've got a Gaussian, and its sigma is square root of n. But its peak is at n. So this is a function that's got a very high peak out at t equals n, and the width of the peak is square root of n. So by the time this function gets to 0, it's incredibly small. It looks like e to the minus n. And so, in fact, you can just plug in when t equals 0, this is n squared over n. It's e to the minus n over 2. So that's an incredibly small number. So in fact, adding the whole negative x-axis doesn't change this integral much at all. So this is a really good approximation that we'll use. And now I've just gone to the answer. So this integral of the Gaussian over the whole real line is the square root of 2 pi n. And there it is, Stirling's formula. The last thing I just wanted to mention is if you haven't seen the integral of a Gaussian before, this is just as Gaussians themselves are important. Being able to take their integrals is important. So just to show you this derivation, what we'll do is write a Gaussian in standard form, which is 1 over 2 sigma squared. And sigma here is called the standard deviation. So you may have heard that in statistics. So the standard deviation squared in the denominator times x squared, that's your exponent. And I don't know how to do this integral, so I'm just going to give it a name, I. And then I'm going to play a funny trick, which is to do I squared. So I squared is just the product of this integral times a copy of itself. And so I don't get confused, in the copy I've changed the name from x to y. Now these are two integrals over different variables, so I can actually pull the first term through and turn this into a double integral, or said differently, an integral over the plane, right? So I'm integrating across x and y. And when I multiply two exponents, I can add the exponents. Sorry, when I multiply two exponentials, I can add the exponents. Great. Now, x squared plus y squared is a very suggestive way to write this. X squared plus y squared in the plane is the radius squared. So I'm going to take this two-dimensional integral over the plane, convert it to polar coordinates. Okay, so there's an integral over theta, there's the integral over r, and remember when you go to polar coordinates, the measure contains both dr and a copy of r. So now we've got this form, and this is a form I can integrate, right? R is going to give us the derivative of the exponent. Since it's a quadratic in the exponent, its derivative is just going to be 1 over sigma squared times r. So I put a sigma squared and a 1 over sigma squared to convert this into the integral du of e to the minus u. That's an integral I can do. It's just 1. And so I'm left with this polar integral, and sigma squared doesn't depend on theta, so I just get 2 pi from the integral, and sigma squared comes through. Okay, so it's kind of a cute trick using the geometry of the plane. And now I've got I squared equals 2 pi sigma squared. So I is just the square root of 2 pi sigma squared. Up here when we were doing Stirling's approximation, n is sigma squared. So this is in fact the value that we get. And just one minor note, here I said x squared, here I said t minus n squared, but this is the integral over the entire real plane. So you can shift the value of x back and forth along, the real axis. So you can shift x back and forth along the real axis. It won't change the value of the integral. Okay, so that's all I wanted to give you for this week. And look forward to next week.